All right, let's get started as I was on mute. All right, so we are, I'm going to go and speak for 2 hours today to provide the material that I need to provide for the class, exactly the same way of delivery as I'm doing in the in-person kind of class. So I'm just going to write some things down. And I should mention that I'm not able to see any messages. So please speak up if you have any question. It's okay to interrupt. Okay, so that's not a problem. So let me make sure that we. First of all, that I'm okay. You can hear me, right? Okay. Can someone speak so I can see if I have a audio back?
We can hear you.
Okay. All right. Great. So I was going to go through first this kind of assignment, which is due on Sunday. The Sunday's assignment is obviously presented last time, and I think from most of the tickets that I've seen, which the TA are kind of responding, people got most of the things correct in terms of the approach of solving this assignment. I just want to um, spend some time. I think I had some notes from another course that I had the same assignment. Hmm, the notes are gone. Okay, so I just want to, and everyone to understand
Yeah.
the two Parquet files that I need to refer to here. So,
Uh,
anyone wants to say something? Yes. Okay. So the first Parquet file is obviously, let me call it the detections Parquet. And obviously, it's a Parquet file that contains detections. Now, you need to spend some time kind of finding ways to extract the frame ID in column number 1. And then in the second column over here, let me call it the detections column. And, frame ID 1, 2, 3. Obviously, this frame IDs corresponds to the segment of the video that the presenter is addressing exterior kind of features of the car and not anything to do with interior. So as I told you before, using FFmpeg, you want to compress this video to clip this video down to, let's say, 10, 15 minutes. I'm not sure exactly the time, how many seconds it is. The presenter presents the exterior features of the car. But this basically Parquet file works on that subset of the video to do the detections. So now the detections in frame number 1, you may have a single detection. In frame number 2, you have 2, 3, 4 detections. Frame number 3, you go back to single detection. So you have the problem of accommodating variable number of detections within a single column of the Parquet file. Now, if you look at the Parquet kind of capabilities, you can actually have a list included in as a column element. So use that in order to avoid the situation where you have the following kind of situation. What is the alternative? So the alternative is to have, let's say, the frame ID, detections, and then you have for frame ID, we have detection 1, let's say, y hat 1. For frame ID 2, we had y hat 1, and for frame ID 2, again, you have y hat 2, you have 2 detections. So you get a lot of repetitions in this kind of column. It's okay to have it anyway, but I think you will be benefiting a lot if you understand a little bit how you can do it in the first option. So let me call them 2 options. All right, so this is basically the detections kind of Parquet file that you are generating using your object detector. And the second parquet file you will be generating is the parquet file associated with the clips. So I'm giving you some kind of structure in that other parquet file, I think, in the assignment. But in broad terms, at a very high level, what we need is you need for every query image. So for query image one, query images are obviously in the images that have included from the second kind of review of the car. For the query image, you have the clip. Okay, so you include here in terms of clip, you can include here the clip that it is associated with the format I gave you. At some point, there is some kind of a YouTube URL with begin and end time. Okay. Now, there is obviously something important that you have to somehow see how you can accommodate. For every kind of query image, you can actually see which video clip out of the total 10 minutes of video is the most appropriate to associate with. That is fine. Sometimes the query images are kind of correlated, and you do not want to have a situation where the clips are heavily, I will call it quantized, in the sense that the begin and end times like 2 frames or something, right? You want to create some form of continuity, if you like, in the clip, as if the clips are for human kind of consumption, in a similar way as YouTube is segmenting their videos into multiple chapters, so to speak, right? So that's the only, I think, complication it's worth highlighting actually over here. So you have how many query images you have? I'm forgetting the number now, but this is basically the second parquet file you need to be generating. And the URL should be clickable in the sense that, well, it should be a properly formatted kind of URL for the one that you're going to be producing. Okay. Any questions that you have on this one?
So for each queuing image, there is multiple classes. So
Yeah, you could actually have multiple classes. So for example, a query image that shows the front page of the car, right? It may have a headlight, it may have a front bumper as well, right? 2 classes, right? So you need to go for both of these kind of classes, right? And find what clip is these both classes are present, right? But make sure that this is what I was trying to suggest with my second kind of comment. Make sure that this is not like something completely transient or something completely kind of random. That typically what the car reviewer is doing. For example, if this is the car, I think it is, and the camera is located over here, right? The field of view, if I remember right, the video. So he's going into this kind of trajectory. He's going from here to here and back, right? So this is basically the trajectory of the camera, right? So for every of the front bumper kind of thing, right? Maybe at some point in the video, right, he will go back, but he will address the engine. He will say something about the engine, which has nothing to do with the external kind of features of the vehicle, right? But it's an engine kind of discussion. So make sure that you first of all segment the video before you start the detections. So you have only the isolated this trajectory, right, of the presenter as he moves around the vehicle. That's the thing. I don't think he goes this way at all, because I don't think he has a camera on that side. So he goes only in one side. Okay. So make sure for all of these kind of classes that you are seeing, for example, that you're returning the clip, which is from here, from the start, when he starts presenting the front of the vehicle until the end, when he goes to the side. And then on the side, he goes into the wheel class, and you have you must have a part from this component. I can't remember now what it's called. You must have a door or some sort or something like that. And then obviously you have potentially few two two three segments over here, and then on the back you have obviously a kind of a pretty dedicated kind of segment that you can actually offer. Okay, so the number of clips that you're going to be returning is not really that large. Should not be a large number. That's my point. Are you following? Any questions? Okay. Yes.
Professor,
Yes. Go ahead. Yeah.
and we're supposed to submit two Parquet files, is that right?
Mm, yeah. The first Parquet file is your detections Parquet file, right? Because you need this Parquet file for. Am I asking you to store it in Hugging Face? I think I am.
It says the one for the video detections,
Okay.
not necessarily the segments, but we can add that too.
Oh yeah. Okay. So, but the segments. I mean, for every query image, you need to tell me the segment, right? So if you want to store it in some other way, that's fine too. But I thought I was asking something to. Okay, let me see. Maybe I'm myself forgetting. Okay, so here's your query images, right? And so what I'm asking here is, okay.
I'm looking at the deliverables
Oh,
section.
deliverables and
Uh,
clips and deliverables. Yeah, a short.
and so you can see it says the one with video detections, but I can make sure that we add the segments as well.
Video detections. Well, that is definitely an omission. I'm glad that I had this kind of discussion. We need to have the clips. Okay. Thought I was asking for the clips further on. Output format required. All detection results developing.
Are the clips kind of implied by the time frames?
The clips are not necessarily. I mean, obviously there is a begin and end in each clip, right? And at some point, I am return the matching clip and its temporal extent. So I'm offering the usual query URL that you inject into, let's say, a document to embed a video clip that starts from 120th second, as you see here, and ends at the 165th second.
Gotcha. So do you want a file containing those?
Either a file or a Parquet file or any other format, since I'm not asking it now, and some of you may already have submitted it. I have no idea if you
Okay.
already submitted it. But I think if you you have the clips, you have the logic for the clips, storing them in a Parquet file is the best thing because someone could even click on that Parquet file in a web interface and see in a Parquet file viewer and get the video clip in a very straightforward way.
Gotcha. Okay. Thank you.
All right, no problem. Okay, so this was basically your assignment. I want to tell you something about assignment 3 now, and I want to tell you something about the plan. Hold on a second. So here we are going into convolutional neural networks, right? And next week we have scene understanding, right? Which is basically object detection, and metrics. And looking at the academic calendar over here, week 6 is week of February 23rd to March 1st. Typically, the March 2nd to March 8th, this discussion about object tracking, which is probabilistic reasoning over time, typically lasts longer than a single lecture because it's a little bit more mathematical discussion, and it introduces probabilistic graphical networks. And it's also the week before your midterm exam, okay? So an assignment 3, if it is given next week, the 23rd, it will be, it needs to cover object tracking, okay? So from that kind of perspective, I'm inclined to put the assignment 3 to be the deadline to be the week of the spring break, okay? So that is basically what's going to happen with assignment 3. I don't want you to be too much concerned with assignment 3 and not prepare for your midterm. So I'd like to offset a little bit the things and offer the possibility for you to provide assignment 3 during your spring break, meaning the Sunday when you come back to New York, March 22nd. I can't remember. Okay, so that's basically what's. So assignment 3 will be given, sent out, but it won't be due in 2 weeks. It will be due in 3 weeks. Okay, that's the bottom line of this discussion. Okay, so let's go back to, unless you have objections. Okay, introduction to AI. Okay, so last time we were looking at these guys over here. We're looking at backpropagation, and I want to cover a little bit spring 26. So we are in lecture 5 today. So we went through constructs associated with fully connected networks. We understood the multi-class classification, the softmax, and we understood some first principles of backpropagation. And I told you that I'm going to do just a very simple backpropagation example that kind of resembles kind of a neural networks to some degree, because the function that we have done, the function we have done was not able to create this correlation. So let me just close the topic of backpropagation with this example. So this is lecture number 5, and today is the 20th. Okay, so I just want to give you a block diagram of, so the headline here is backprop continued. So this is basically W transpose X, giving us out as Z, passing it through a sigmoid to create a Y hat. Okay, and so X is coming in, and W is the parameter vector over here. And the question is calculate the gradient of Y hat with respect to W when W is equal to W0, W1, W2 is equal to 2 minus 3 minus 3. Okay, and X is equal to X0, X1, X2 equal to minus 1, minus 2, minus 1. Okay. So the first thing that we do, obviously, is the forward pass. And I'm sure most of you will be able to answer this kind of question. What are the two equations of the forward pass? Well, it's almost like the block diagram. The first equation is basically Z. Well, obviously, there's no underbar in Z. So this is just Z. So Z is equal to W transpose X. That's equation number 1. And the second equation is Y hat is equal to sigma of Z. Okay, and this is equation number 2. Okay, so equation number 1 needs to be evaluated. So as I told you, in forward pass, we need to have a value behind every tensor. of the forward path. So therefore, z, if you do the equations, z is going to be, if you do the calculations, that is, z is going to be equal to 1.0. Okay. And if you do the calculations here, sigma, not sigma, but y hat is going to be equal to 0.73. Okay, fair. I hope everyone is okay with respect to this trivial kind of passing in the forward direction. And then the second pass is coming, which is the backward pass. And the backward pass means that I need to start drawing now the first downstream gradient over here. Then it has to go through the sigmoidal gate. It gives me dz. Then going to go to here to do, to give me the d w, that is, and the dx, okay, to for this kind of a dot product kind of gate. And you need to be also kind of careful here to not calculate something that no one is asking you about. No one is asking you about, right? So you need to calculate something which is associated with which vector over here. Well, ultimately your destination is this guy. The answer, the question is associated with this guy, right? So it is basically the partial derivative of y hat with respect to w0, partial derivative of y hat with respect to w1, and with respect to w2. Okay, so as we discussed, we are going to do the first trivial calculation. Last time we did exactly the same thing with the function f. So we did dy hat is equal to the partial derivative of y hat with respect to y hat, and this is equal to what? This is equal to 1, obviously. Then we did the dz is equal to, well, the template was the upstream gradient dy hat, the partial derivative of the function of the gate. The gate, it's the function of the gate is executing, which is sigma of z with respect to z. Okay, so this is now 1. Now this guy, you will never be able to find it in any lookup table. However, in lookups that are involving kind of a neural networks, the symbolic calculations that I was telling you about, backpropagation is known to engage in order to become more efficient. This is obviously a very popular kind of entry there, and if it comes to a question in an exam, we will always be giving you things that you will not be able to find in a lookup partial derivatives lookup table that I told you exists in the course site, and you need to have it with you. So this partial derivative is 1 minus sigma of z times sigma of z, okay? And this is equal to 0.2 if you do the calculations there, because you know z, therefore you know how to calculate sigma of z, and that's the end result of the dz, okay? And now something that I wanted to refer to that was not present in our previous kind of discussion is the dw, because this is what we are after, okay? So the dw, it is dz, which is the upstream gradient into the dot product. And then you have partial derivative of the gate itself, w transpose x, with respect to w, okay, which is now a vector, okay? So this dw thing is a little bit strange now, but will end up being something kind of fairly simple to calculate. So we have partial derivative of something which is a scalar with respect to a vector. Okay, so we need to expand this. So this is now partial derivative of if you expand this w transpose x, it will be w0x0 plus w1x1 plus w2x2 with respect to w0. Then we have partial derivative of w. I'm not going to write it again because I'm sick and tired of backpropagation. So I'm just going to enclose it in parentheses and this sign means that is identical to the term that I actually wrote over here in the first kind of part. And this is now with respect now to W1. And then this is partial derivative of, again, exactly the same guy with respect to W2. I hope you're following, and I don't have any visibility because of the remoteness of the lecture, but I hope everyone is understood what's just happened there. Then I will show you some formulas where these kind of expansions and are automatically kind of taken care of. But looking at the first term over here is 0.2. The first term, there's only W0, only the first term over here in the partial derivative, right? So it is, the end result is x0 plus 0 plus 0. So there are two other terms, but the partial derivative of W1 x1 with respect to W0 is 0, and the same thing happens with W2 x2. I hope you got that. Then we have over here 0 plus x1 plus 0, and finally we have 0 plus 0 plus x2. And therefore the outcome is 0.2 x0, x1, x2. And this was basically the answer if you do the calculation. Well, the question required to tell us the tensor of dW. It's minus 0.2, minus 0.4, and minus 0.2. And that's the end answer. One thing to note here, no one is asking you anything about this dx. So make sure that if a question arrives in your desk, such as this, you don't go into do things that are not associated with the question they're asking you. Okay, so any questions on this simple application in this kind of a trivial neuron for backpropagation? As you will see, this kind of example is not given. It's not a coincidence. As we'll see when we discuss a little bit about regularization, I'll bring up the topic of regularization in neural networks at some point where I'm discussing batch when I'm discussing normalization, I mean to say. When I'm discussing batch normalization and layer normalization during the transformer kind of discussion, I'm going to refer to this kind of specific moment in time when we looked at this neuron, and I'm going to refer to specifically the outcome of this DW there, because it plays some role in explaining what is going on with normalization in general in the neural network. So keep an eye on this page. We'll refer to it a bit later. Okay. All right. So this was basically, so going back to the site now, I cannot draw all these kind of equations, but I have here a couple of references. So first of all, remember I was telling you that everything is symbolic at the end of the day. Well, in a very similar way as we have defined lookup tables for trivial gates like additions, multiplications, divisions, and inversions, and things like that, just like the lookups that we did last week. In a very similar way, people went ahead and created the lookups for the gates, which are very frequent in neural networks. For example, it's very frequent to see a matrix by vector multiplication. It's very frequent to see that being followed by softmax, and even more frequent to see that being followed by cross entropy. So all of these kind of patterns that you see in various neural network architectures have been tabulated, have been pre-computed, if you like, and gradients are able, being just looked up in a very similar way as we have just done last week. So, for example, take for example the last gate over here, which is a combination of individual components, but in terms of backpropagation, because they all come together, they are being met together. For example, someone may ask you, what is the gradient of the loss with respect to Z, which is the input to the softmax, the logits, right? So it is y hat minus y, and that's a symbolic result that you are free to use without any further explanation. Okay. It's very unlikely that someone in this course will ask you to backpropagate manually a new complicated kind of neural network. You may face a small backpropagation kind of question, but I'm just telling you that this is what really happens. This is how the symbolic calculations are happening in the local gradient calculators. And of course, the parallelism that exists from the individual kind of gate independence is still there. Okay. So I'm not going to spend more time into this into the backpropagation kind of story. However, I should also mention that understanding a little bit about backpropagation helps because you're able to understand sometimes the behavior of networks during training or the justification of why certain componentry in the neural network has been revisited. For example, I refer to the replacement of the sigmoidal units inside the bodies of neural networks with ReLUs. This came straight out of the backpropagation experience or explanation of the behavior of the sigmoidal units as their derivatives have very, very long zero tails. Okay. So it is those discussions that involve gradient flow and empirical experience that led to specific choices in the architecture of this kind of neural networks, as we've seen already sometime last week. Now, so this discussion kind of opens up the following kind of topic, which is what is the next step? Okay, we understood a little bit about fully connected kind of dense layers. How we actually going into process, let's say, other modalities that we frequently need to process in AI, and this includes computer vision. So I'm going to gradually go into an application domain, which is the computer vision topic. And with that, I'm going to cover today convolutional neural networks. And the next week, I will use these convolutional networks to build object detectors. Okay. So so we're entering, if you like, the perception space. And one of the things that maybe, I don't know, typically I had some image over here. Maybe in this new site, this image kind of disappeared. So first, let me just start writing then. Okay, so this is perception, and more specifically computer vision, because obviously we have perception using other sensory architectures than cameras. So obviously, just from starting from the basics, we are going to have an image of 8 pixels by W. And as we discussed before, up to this moment in time, in order for us to process it with a neural network, what we had to do is we had to flatten it, right? So to create, if you like, some kind of transformation where this image was basically a vector of r to the power of n. Now, this will not longer be the case. We will invent a certain kind of neural structures, and we'll introduce now the concept of a convolutional kind of neuron that is able to do the processing of the image as an image, providing other images as an output. Okay, so we'll call these images feature maps, and let's take an example of that just to motivate the discussion a little bit. So let's imagine that you have the following kind of problem. The following kind of problem. Come on. Let me open up my notes. At least I know what to draw, but go out of memory. So let's assume that I have a problem like this. So I have some some kind of a time series plot that shows, if you like, a signal as it is observed on the time axis. So I have something like I call x of t. And let's assume that this is 1. It's like almost like a digital pulse, if you like. And someone is asking you the following kind of question. Find the location of the pulse on the t-axis. Okay, so anyone like to offer any ideas on how to solve this problem? Yes, we are not together. I'm going to suggest a fairly simple kind of implementation of a proposal. Okay, so I didn't even finish the question. Find the location of the pulse on the topic, assuming you know the exact shape of the signal. Okay, so the exact shape of the signal, you know exactly that is a rectangular kind of thing, how much is its duration, and so we know the template of this guy. Okay, so knowing, if you like, the template of this guy, we're going to use that fact that to our advantage, and we're going to go in this kind of starting from. So imagine that this thing is a buffer, and we're starting from some kind of a buffer location over here, buffer location 0, position our template over here, and we do the following kind of operation. We take the product between x of t and y of t, and for every value of that x of t and y of t, and we can assume that we have some form of digitization kind of done. So we are dealing with kind of discrete kind of values. So the same thing can be done here as well. We are making the product, and we sum all the products together, the product terms together. So if we do that, we will actually get into the output will be a 0. Because obviously there is nothing over here in this space, right? So there will be nothing, and therefore the output will be 0. So imagine that you slide this guy in to the right, let's say, by one memory cell, whatever that is. You get exactly another 0, another 0, another 0, and so on. So you can understand that as this guy now starts moving into a space where this x of t is located, it will start having some kind of partial overlaps. So at some point, it will start offering some kind of a non-zero correlations, as we call it, the operation. I'll show you a plot in a moment. And as the guy now, right at the peak, we're going to get a peak where this pulse is right aligned with the x of t. And then after that, we will start getting again some kind of reduced kind of correlations all the way back to 0 for all the other future positions of y of t. I hope it was a kind of a trivial example, but you got what it means. And so really at this kind of peak, when we get a kind of a peak correlation, we are offering to be their answer that, the pulse is centered around here. So this kind of a simple, kind of a trivial kind of operation, which is a cross correlation operation between x of t and y of t, is what is the essence of convolutional neural networks. So we call them convolutions, and convolutions are correlations, but they are implemented as correlations in practice. And we're correlating effectively something that is at the input. So x of t is going to be our input, which is going to be an image in a few minutes, and y of t will be something we believe that is a good template for us to pick the right pictures out of this image. Okay, so if you understood the one-dimensional kind of situation over here, we will now try to understand what happens now with images. And so here's the two-dimensional kind of a story. The two-dimensional kind of story involves a black and white image that has some form of a vehicle. Okay, so that's some form of a vehicle. And someone is actually posing exactly the same questions. Can you locate this vehicle in the image? And but this time they are not giving you the template. Of course, if they give you the template, in other words, the exact shape of this kind of vehicle, you could go around and start correlating with the exact kind of template, and that will actually be fine. You'll be able to detect the location. However, there are two major problems. The templates and the correlation with exact templates may be expensive operations because you have to have the whole feature set of the whole template, if you like, of the vehicle to correlate with the original kind of image. And the second is that any slight deviation from which is more serious, the second kind of part, any slight deviation from the original kind of template of an image, for example, an SUV versus a sedan, may actually create a quite poor output. So we're trying to come up with an approach where we get some kind of a feature extraction generalization using much smaller templates, which we'll call kernels, and we'll expand them to have 3 dimensions, and that structure is called a filter. Okay, so you can imagine someone suggests the following kind of approach. I am going to come up with a good patch content. These patches are kind of small, 3 by 3. And since the image is black and white, so remember black and white images have sort of 0 to be black and 255 to correspond to white. And why this 255? I think I explained that in the first kind of lecture. 255 is associated with 2 to the power of 8 minus 1. 8 is the number of bits that we assign to each pixel. So here we have just a single channel. We have black and white image. We have 8 bits of dynamic range per pixel to represent, if you like, the light intensity. And so the absolute black is 0 and the absolute white is 255. So if I want to detect this area, the roof, let's say, of the car, I would definitely shade this to be white, right? Leaving the other two sort of black. And imagine I will take this kernel and I will. Oh, I didn't even draw the 3 by 3. Okay, so I'm going to move it like this. Start from the top left corner and move it to the side on the side over here to finish this kind of part of the image. Then I'll go to the second 1 pixel down, for example. And at some point, I will arrive over here. And right there, what's going to happen? I hope you can see it. The white sort of feature of the roof of the car will actually correlate heavily with the white contents of the patch, and therefore create definitely a strong feature at the output. Okay, I hope you can see that kind of trivial sort of situation we are facing in. So this 3 by 3, this kind of kernel is going to pick up the roof, is going to pick up the hood, is going to pick up the floor of the car, whatever, whatever features are present that are like flat horizontal lines are going to be picked up by this kind of kernel. But as you can see, we don't need only one kernel to pick up sort of all the features present in the image. An image is a fairly rich kind of content-wise, so we need definitely multiple kernels. For example, to pick up something which is associated with this guy over here, definitely we need some kernel that looks like it. So we put a lot of weight on the diagonal over here, and this will be pick up features such as this. The other diagonal is going to be needed for picking up features on the other side. You get the point. I mean, it's a trivial kind of point, but I'm just mentioning it here. So, for example, over here, the wheels will be picked up by some other kind of pattern. Like, for example, the wheels will be picked up by, this guy over here, potentially, right? So these are all kind of each of these kind of guys will be calling a kernel, and the composition of these kernels, which are, let's say, 3 by 3, vertically stacked together. This structure will be called a filter. So this filter is going to, in general, for multiple, for of course, for images that have the appropriate kind of depth, is going to be used to extract features for that are compliant, correlated heavily, if you like, with the patterns, the spatial patterns that the kernels kind of contain. Now, these patterns are predetermined, if you like, by us, but ultimately, these patterns will actually be, in the case of neural networks, convolutional neural networks, as we call them, going to be determined automatically via the training kind of process. So the training process will actually determine the patterns themselves rather than us using this kind of toy example here did just to show the sort of demonstration of what a correlation is doing in the two-dimensional plane. You have any questions on this discussion? Don't hesitate to ask questions. This is the time to ask questions. Any question I can explain.
All right. Could you clarify what the filter is? So the filter is just
So the filter is going to have two 3 dimensions. It's going to be a volume. There's going to be has a spatial extent. So this is basically the 3 by 3. Let's say we call it the spatial extent, and obviously there will be the depth, and we'll see that the depth of the filter is going to be related to the depth of the input feature map. Okay. Did I answer your question? You're okay now?
Somewhat. So
Yeah.
there's multiple kernels in the filter. Is
Correct.
that like,
That's
are these
correct.
the different patterns that we're detecting?
Different patterns, and the different patterns are going to be results of a training process rather than a priori kind of set as it in this case over here.
Yeah, got you.
Any other questions? Okay. All right. So what we will do now is we will go back to your site over here. And I'm just going to go through the operation as we have just seen it, okay, and what it does mathematically, right? So what is really the operation of correlation, spatial correlation operation in practice? So I have over here a trivial input image of size 3 by 4, and I have a kernel, a filter, in other words, with just a single kernel of 2 by 2. Okay. And I'm starting from the top left corner of the input image. At every moment in time, I'm doing a correlation operation. Well, the correlation operation in the spatial domain is a dot product. Therefore, I'm going to multiply A times W, add to it B times X, add to it E times Y, then add to it F times Y, and I'm going to spit out for that specific location a scalar number, as you can see. Then I'm going to go one position to the right, Then I have a new location with new contents of that input image, and I'm going to spit out yet another scalar number. And yet another scalar number. So I am done with the first row, if you like, or the first two rows of the input image. And then I'm going to go down 1 pixel, and I'm going to do exactly the same thing. So there are two obvious things that are happening. Apart from the fact that I am having apart from the fact that I'm having a scalar as an output in the what is called an output feature map. The size of the output feature map is always smaller than the size of the input feature map, except from one case. And the one case that it is equal is when the patch or the kernel has size of 1 by 1. When the kernel has size 1 by 1, I have as many pixels at the output feature map as input pixels. And but in all other cases, there will be lower number of pixels. Okay, and we will see an equation later on that defines various hyperparameters to the size of the output feature map. Okay, so it's a deterministic calculation on what is the size in terms of height and width of the output feature map, which you see at the lower part of this image. So the output feature map here is 2 by 3. The input feature map was 3 by 4. Any questions on this? Anyone? Okay, so the other thing that I wanted to mention is that we've seen the kind of a concept of a filter as a structure that does the dot product in a 3D in the volume space. We always going to have volumes in this kind of neural networks because we always will be dealing with input and output feature maps that have some depth and some kind of spatial extent. And a couple of things that I wanted to cover here is two hyperparameters that are architectural parameters. I don't want to call them hyperparameters necessarily, but architectural parameters is the stride that resembles what you intuitively understand as stride when you're walking. So you have a stride of 1, you're visiting every pixel, you're shifting to go to a new location as we have just did by 1 pixel. You have a stride of 2, you are shifting by 2 pixels, 3 pixels, and so on. Typically, strides are symmetric between horizontal and vertical, between height and width kind of dimensions, and they are typically small numbers. And as you can see here, you have another parameter which I want to mention. This is the padding parameter represented by a small letter p, and the padding parameter determines how much padding we have. This means value of 0 pixels we have surrounding the input image. So we'll see. We need to discuss now why on earth we have padding and what purpose does it serve. Before I go to the padding, though, just want to make sure that everyone understands what we are showing over here. You are showing the output feature map, which has been created from a filter of depth 1. There's only one kernel over there in that kind of filter. As the filter is observed in multiple 3 or specifically snapshots in time. Okay, when it is in location red in the lower image of the input feature map, it will create the red pixel of the output feature map. When it is in the blue, it will create the blue, and so on. Okay, it's a straightforward kind of thing. It's not really something difficult to get. It's just some kind of a sort of processing that is happening. We will see very soon a more complicated case that requires some kind of drawing from my side, but right now things are kind of simple. So coming back to this kind of padding, the padding is definitely a tool that we are actually going to be used to achieve 2 purposes. One is a secondary, but here's the primary kind of purpose. As I said, the output feature map is going to be always smaller than the input feature map. Without padding, if you take the equation, which I'm going to show you in a few moments, and you apply it, every single output feature map needs to become an input feature map for the second layer and so on. What you will see without padding is that the shrinkage of spatial dimensions is quite a lot. And so padding is going to help us to manage the dimensionality reduction that we're getting in the spatial coordinate, in the spatial extents of these feature maps. That's one thing that it will achieve for us. So here we see the sort of a situation where we have no padding and we have padding, and how for various sizes of padding, how much the output feature map kind of dimension is affected. And as you can see, it's quite a good tool to manage the reduction. Why we have to manage the reduction? That's another question. Well, we have to manage the reduction because if you shrink too much and you have now spatial extent of 7 by 7, as we'll see in a next example of an actual CNN kind of architecture, then there's no point of continuing the convolutions, right? The correlations. So just like what we have seen earlier in dense kind of layers, we want to have more gradual projections, if you like. So we need depth to perform well. Okay, so because we need depth in the number of layers that we need to support in a CNN, we need to have the tools to manage the depth. We don't want to run out of spatial dimensions very soon or too soon. And the second kind of role, which is a secondary kind of role that the padding kind of sort of buys us, is, as you can see, without padding, that yellow patch, sorry, not that red patch would have been only going to be able to be in one position at the edges of the image. While with padding, that yellow, that red patch, that red kind of kernel is going to be able to move around and therefore offer its contents, correlation contents with a variety of positions in that kind of input image. So this padding actually also buys us some kind of improved performance because at the edges of these images. Okay, so that is basically the role of the two kind of parameters there. One role is to reduce computational complexity, the strides, and the other padding is also to manage the depth of our CNNs. There are some animations here which you can also watch on your own, which of course brings us now to the most interesting kind of question. Okay, we have seen the diagram, we have seen the equation, the dot product, but what really exactly is happening inside the CNN at a specific snapshot in time? What is being generated in terms of an equation? So I'm going to go towards that kind of direction to describe it. So I'm going to title the discussion the snapshot of a CNN layer operation. So as I told you, the general kind of case is that I'm going to have an input feature map, which is obviously a volume. And this input feature map will have some kind of a resolution in terms of pixels. Maybe this input feature map came straight out of the image, therefore the depth will be 3 over here, but in general the depth will actually be called ML minus 1 here. And if it is the very input of the CNN, it will have as many pixels as the input image. But over here, I'm going to generally call this HL minus 1. And this guy I'm going to call W. L minus 1, the width. Okay, so I hope that that's basically the input feature map, in the general kind of form of an input feature map. Now, the input feature map will at some point become an output feature map. Okay, so the output feature map may have any depth that we want to design. So that's our design parameter, ML. Okay, and it will have an HL and will have a WL. Okay, now, so the snapshot of a CNN layer operation, what is a snapshot? Well, a snapshot in time. Well, in obviously in a specific snapshot in time, the filter, which is let's assume that the filter is right here. Okay, it's located right there, and it is obviously is going to create, as I told you, at this specific snapshot in time is going to create a scalar. It's going to create a dot product. And my question to you is, what should be we fixed the spatial extent of the filter to 3 by 3, as you can see here. It's 3 by 3, typical size. What should be its depth? What do you think is going to be its depth? Does it need to be shallower, deeper, equal to the input feature map depth? What do you think? So there are three options, right? The first option is to be deeper. Well, it doesn't really make a sense for the filter to be deeper than the input feature map, because what is going to correlate with? I mean, there's no content to correlate with the additional kind of depth of the filter. Shallower, for the same reason, the filter is not going to going to leave money on the table, so to speak, in the sense that it will not be able to pick up content from all the dimensions in the depth-wise it cannot reach. So the only reasonable, obviously, thing to have in terms of the filter is going to have exactly the same depth as the input feature map. Okay, so now, provided everyone is happy with that, this specific the resolution of the output feature map now, the resolution of the output feature map is smaller. So I'm going to draw it to be smaller than the input feature map. Okay, and at this specific moment in time, the I, jth location of the output feature map is colored. I, j is the spatial extent, right? So first of all, we need to understand what is the output pixel, that where is going to be this output pixel. And also we need to understand where is the other output pixel after the filter moves in the next snapshot. Okay, so that's the two things that we need to answer in order to understand how the CNN is working. All right, so let's see. I'm going to take the pixels of this column of the output feature map, and I'm going to rotate them 90 degrees. Okay, and all right, so this is basically how many pixels I have? Well, I have definitely ML pixels. And I'm going to introduce this is basically your I, jth kind of column. So let's put this over there. And I'm going to introduce an index from 1 less than or to KL less than or equal to ML to identify the pixel, okay, in this column. Obviously, the KL value will identify uniquely that kind of pixel. And I'm going to also do this exactly the same here for the kernels. So I have the kernel over here, another kernel over there. I'm just basically drawing the filter, but in a kind of rotated 90 degree and write down draw all its kernels. So I'm going to have V and U as the coordinates of the kernel, and how many I'm going to have for those guys. I'm going to have obviously ML minus 1. Please interrupt me if I don't understand what's going on here, okay? So I'll explain it once more. So it's 1 less than of KL less than or equal to ML minus 1. KL minus 1, that is, it's a different index. KL minus 1. So KL minus 1 points to a specific kind of kernel of that filter, okay? And as I told you earlier, all of the filters, all of the kernels are going to be involved in determining what? You told me the end result is going to be a scalar, right? So I am going to draw this scalar green. Let's assume that this is the scalar that they are, the filter right now with its correlation between itself and the overlapping volume of the image at this specific snapshot in time results into that green pixel, which I'll call this green pixel Z of I comma j, because it is located in the I comma j kind of coordinate, and KL, which is the some depth in that kind of column. Okay, so here's the pixel. Okay, that's one thing. All right, so let's write down the volumetric correlation, right? Okay, so Z of I comma j comma KL is equal to, remember what was happening a few moments ago. What was happening a few moments ago, we were looking at a two-dimensional kind of space, okay? And in this two-dimensional kind of version of the things were kind of straightforward. The filter had just one kernel. This guy was moving around. A dot product was being formed. And in terms of equation, this was basically the equation. You had two summations. And now we are going to have, obviously, we are going to have three summations. So the first summation is going to be over the U and the V extents of the filter. And the depth dimension of the filter, which is identical to the depth dimension of the input feature map. And the correlation is between the overlapping portion of the image, I plus U, J plus V, comma, KL minus 1, times W. I will call W the contents of the filter, U, comma, V, comma, KL, comma, KL minus 1. So these W are going to be, as I told you earlier, the filter will no longer have predetermined kind of patterns, but they are going, it's definitely going to have trainable parameters. So these W's needs to be specified, changing obviously during the training kind of process. And after training, they will end up in whatever W star value they're supposed to have. So now this is the big question here. So this is the situation. I have a filter is doing its thing, and it is determining, things that are happening in the sort of with its three-dimensional kind of operation between itself and the input volume defines this green pixel. The question to you is the following. Let's assume that the filter moves now in the next snapshot, moves here. Okay? It moves here, 1 pixel to the right. Can you tell me where is the magenta pixel? I'll give you 2 options. Magenta pixel is this. Magenta pixel is this. 1 or 2?
Two.
You said 2? Okay. Anyone else? Anyone else anyone else for this is 1 and this is 2? Anyone else for 1? Okay. So the right answer is that's great. The right answer is 2. If I can go back to what I was doing, of course. Okay, so this is the right answer. So the pixel which is going to be thrown when the filter moves to the right is the pixel next to the green. In the same, this is the most important part of this discussion, in the same depth, KL. So as you move the filter around 1 position up, you plot another pixel on the same depth of the output feature map. Effectively, by repeating this over all the possible locations that the filter can take of the input feature map, you are effectively plotting a single slice of the output feature map. Okay, so let me write this down. So the one filter plots one slice, a single slice of the output feature map volume, which of course begs the question. That's point number 1. How we are going to get an output feature map? Because right now we only got a single slice of the output feature map. Anyone has any ideas? How are we going to get the totality of the output feature map? We need ML slices. And the answer is we need ML filters. Okay, so the end discussion ends up being a realization that a single filter is not able to compute the whole output feature map. We need multiple filters to achieve that. Okay, these filters, for this reason, they are going to, not only for this reason, but these filters, you should think about them as the equivalent of the sigmoidal neurons that we've seen earlier. Now they are called convolutional neurons. Their operation of the W transpose X that we've seen earlier is actually shown here as a dot product at the volume now level. So it's a three-dimensional kind of dot product. They do produce the scalar, and we will use exactly the ReLU nonlinearity again to take this kind of dot product and pass it through the nonlinearity. Okay, so in terms of structure, yes, go ahead. Anyone else? Anyone had any comments? Okay. So in terms of structure, we are not going to see a significant kind of change here, but we need to understand a little bit more how we are going to use these multiple convolutional neurons to. So I'm going to show you an animation of how a simple example, which is basically what I drew, but with an animated kind of flavor. Okay. So here's the example. So you have where is the example? Okay, here's the example. So you have a general kind of situation where you have an input feature map of 7 by 7 by 3. And you want to form an output feature map of whatever spatial extent is. They're all deterministically determined from, I'll show you the equation in a moment, from your input feature map size, the padding, the stride, and the kernel size. Okay. So it ends up being 3 by 3, the output feature map, which is green in this case. And you design a system where you want to have size 2 as the depth dimension. Okay. So you could have a 3 by 3 by 10. 10 will be your choice. Doesn't matter, but it is 2 here because obviously it's a limited kind of space to implement the animation. Okay. So what we have just drawn in just now, a few moments ago, were this situation. You have a filter, which is the dark blue over here, sitting on top of the input feature map. And at any one instance in time, the filter has some contents. These contents are, of course, determined out of some stochastic gradient descent kind of driven kind of training kind of procedure. They have some contents. These contents and the dark blues are correlating with each other, the three-dimensional correlation I wrote, to determine the boxed scalar that you see on the first slice of the input feature map. Since you have 2 output slices, you need 2 filters, filter W0 and filter W1. This is the reason why I have 2 of them over there. And as you notice, filter W0 is involved for the first slice and definitely is not involved for the formation of the second slice. For the second slice, only the second filter is involved. So that is basically the whole sort of story about a convolutional operation inside that kind of layer. The filter will move around, will do the correlations, will form some output volume over there, and this output volume will go through nonlinearities in order to give us, if you like, the richness of representations that we required from the dense layer states as well. And nothing changes there. And any questions that you have on this? Questions? Okay. All right. So another thing that I wanted to highlight is this equation over here. This equation is the equation I was told you that gives you the output feature map spatial dimensions. So height is the input feature map height. P is the padding parameter. K is the kernel size. And S is the stride. And this strange parenthesis is called a floor operator. And you add the 1. And that will give you the output feature map height. Exactly the same equation is applied when you are on the width dimension. But you have to replace everything with the width kind of parameters. and now you have the output dimensions for every layer. You need this equation sometimes in an exam setting. Sometimes you will be asked to design a neural network, and I think it's a good idea to write this equation down. Okay, all right. So let's now move on a little bit on what we have to bypass this positive discussion. And I want to spend some time on the pooling kind of side, on the kind of some other components which are present in our kind of typically in this kind of networks. The pooling layer is actually kind of a typical kind of present in several kind of architectures. And what it does is, as you can see, it is applied. Let's say in this case, it's basically is applied for an input sort of image, just like the correlation operation moves around. But instead of doing correlation, we apply a function in order to determine the output value. So max pooling, which is actually shown over here, if the input the input feature map had values of 1, 5, 3, and 2, with max pooling, 5 will survive. Effectively, the intuition behind it is that you're picking up the most important features that resulted into strong correlations, in other words, from this kind of correlation operation, and therefore you are filtering out irrelevant potentially features or very weak features that you don't want to propagate in the forward pass. So this was basically the max kind of pooling, kind of a typical kind of component that we see sometimes. The other component that we see regularly, sometimes we see this one-by-one convolution layer. It's not entirely intuitive as to what it does, especially why this, if you see it, what it does, it just basically moves from one pixel to the next. And I think it's worthwhile to look at the three-dimensional kind of situation, to draw it exactly in the three-dimensional situation, and then it becomes apparent what is happening. We are fairly frequently meeting this component at the termination kind of stages of a neural network, or when we want to do some kind of dimensionality kind of matching, as in residual kind of networks. And we have over here again a filter, but this time the filter is one by one and has, as we discussed, the regions of the same depth as the depth of the input feature map, obviously, which is shown here in blue. So as the filter moves around, it starts coloring a slice, as we just discussed. But effectively what it does, it basically combines all the depth information that was present in perhaps all the previous kind of convolutions that happen in the body, if it is located in the termination kind of in the final stage of the network. And then we have now a matrix in our hands, and we can take this matrix, we can flatten it, pass it through fully connected layers to do dimensionality matching with a number of classes that we need, and so on and so on. So that's another common component in convolutional networks. So don't be sort of feel foreigner to things like if you see a one-by-one filter. I want to spend some time on a typical kind of architecture and explain another pattern which is now observed not within the layer, but across layers. So more specifically, the pattern, and that answers the questions also as to why we need more depth. Why, in other words, this ML is increasing as the depth of the network is increasing. Okay. So here we see, if you like, a network This network processes 224 by 224 sized images. And as you can see, the third dimension, which is a depth, is increasing. 64 becomes 128. Then we are having a 256. Then we're having 512. And then we kind of terminate the network, right, where we run out of spatial dimensions. So two things are happening. The spatial dimensions are shrinking. Well, obviously, they will shrink despite our presence of padding. As you can see from that equation, there will be reductions. It's just with padding, the reductions are a bit more manageable. The depth dimension is increasing as the layer is becoming deeper and deeper. So the question is why that is a kind of a common pattern that we see in these kind of layers. And the answer to this type of question is that effectively in this kind of networks, and there is some kind of exercise along these lines as to what these networks are learning. And the initial kind of layers are very much topologically, geometrically aware. In a sense that the what they learn is basically patterns that are very much associated with topology and geometry. So simple patterns that are also present as features that we distinguish images from one from another. As humans distinguish images one from another, are definitely the patterns that these first layers are kind of absorbing. However, subsequent kind of layers are becoming less and less attached to geometrical shapes. And they are effectively need to combine these kind of simpler patterns to form more complicated ones. And the next patterns will be even more complicated than the previous ones. And so the many combinations, if you like, of patterns, kind of combinations that are needed by it means more filters. And this is the reason why we need effectively significant number of filters to do this kind of to accommodate this type of combinations. So we are also with the depth dimension, if you like, we are also increasing the number of parameters associated with the specific layer. So the two things are certain here in any kind of architecture. At some point, you will run out of spatial extent. And the point that we run out of spatial extents is the Con5 layer, right? And after the max pooling operation, we have 7x7. And this is basically the bottom line. We cannot really do any more convolutions. So what we do is we will flatten the 7x7x512 volume. We'll flatten it into a long vector, and we will pass it through fully connected layers. So we will pass it through FC6, then FC6 will pass it through FC7, and so on and so on, gradually moving towards the required dimension of our logits. And the required dimension of our logic is 1000. That is an ImageNet kind of data set, which has 1000 classes. And that's how we do the sort of dimensionality matching. And then, of course, the usual componentry kind of follows, the soft maxes of the world and the cross entropies and things like that. So this kind of network is a typical kind of network that, however, had some kind of issues in terms of not being able to scale with respect to depth that much. So it was limited to a very small number of layers, maybe 16, 19, that's kind of order. And one researcher in 2015 provided some kind of a solution, some kind of an architecture that solved the scalability issue in terms of depth of the convolutional networks as a whole. And this gave rise to residual networks, right? So as a title, is residual networks. So we need to study a little bit this architecture as well in order to get the whole grasp of how we are actually creating features or representations out of images. Because REST nets, as we're calling them, are like the bread and butter of representation of picking up features, of which featureizers, as we call them. Okay, so let's before we go into this kind of RESTnets, the website has some kind of a small notebook just to make sure that you are familiar with this kind of architecture. Obviously, this is not a PyTorch kind of code. I'm in the process of moving into PyTorch, the website. So, but the bottom line is not really to stick to the specific kind of framework, but just to understand the primitives that we just discussed in a little bit more Pythonic kind of way. So one of the things that I want to highlight is in terms of API, typically you will see this 32, 64, 128. Remember the pattern I was telling you, the number of convolutional neurons, therefore the depth of the output feature maps is increasing as the network depth is the network depth is increasing, right? So the deeper you go, you're deeper in terms of feature map dimensions you need. The other obviously parameters, the 3x3, you're familiar with it. These are the special extents of the filters, and the activation functions, as I also told you, they are maintained to be ReLU. You have a max pooling layer. That's a very common pattern. Do a convolution, maybe one after another, and then do a max pooling. Here we are doing conv, then followed by max pooling. We'll pick up some significant features out of this convolution. And then at some point, if you notice over here, you will run out of special extent. You don't notice it in the API here, but you will notice it when we look at the table of output feature map dimensions. And you will decide to flatten because you decide now to terminate the network with a head. Okay, so the first thing that you do is forget about dropout. Is a specific kind of function or capability to do regularization, and I'll explain that at some point. But if you look at the head over here, what happens after flatten, you have a dense layer with 512 neurons. Okay, so you have a dense layer that is definitely not a head, okay, and provides a 512 dimensional sort of feature vector to the head. And it should not be any surprise there. The specific use case is a binary classification use case. The last layer is the dense layer of a single neuron who has a sigmoidal nonlinearity because we have binary classification, and is dot producting this representation from the previous kind of dense layer in order to form the scalar that it needs to provide the posterior probability of the positive class. Okay, so this is basically a classic kind of architecture in terms of the CNNs. Now, if you open it in Colab, I believe you can actually also run it. And I need to add some more. I think the scripts that I have right now have either become lazy or they have forgotten to add the outputs. There were plenty of outputs here for this specific notebook. I'll take a look potentially tomorrow to see if I can retrieve them. Okay, this is just basically cats versus dogs. Two classes, two sets of images that were classified with CNNs. Actually, it's a relatively good notebook to look at, especially if you're getting started. So I want to spend the last few minutes on residual networks, which is, as I said, is really the bread and butter architecture in terms of featureization. And this will actually give us some kind of touch points with backpropagation that I want to mention as well, and close the discussion for today. All right, so let's see. So this is, I'll call this headline ResNets. Okay, so what is really a residual network? So as I discussed, the motivation of introducing, if you like, residual networks was the fact that the previous architectures, like the one I just showed you a few moments ago, were not able to go deep. And a simple kind of change in the architecture provided certain capabilities, which I would like you to understand, why these capabilities provided the performance advantages that we've seen today in residual networks. So what I will do is I'm not going to write down convolutions over here, but what I'm going to abstract all this kind of convolution and max pooling kind of operations as function F1. And I'm going to have a very small RESTnet. So what is a RESTnet? A RESTnet is a network that not only takes an X, for example, which strangely enough, because of my notes are written this way, I'm going to call this input Y0. But it takes this Y0 and without doing anything to it, it adds it to the output of F1. Okay, F1, again, remember, it's a block that contains potentially multiple convolutions and max pooling kind of operations, of course, with non-linearities. Then the output of that, I'm going to call it Y1. And I'm going to take this and to, in a second, let me do it. Can you hold on just 1 second, please? Okay, so we do exactly the same. The pattern is not really changing. And we are going to do this. Finally, just 3 is enough. Y3 is here. Y2 is here. So these are called skip connections. And they completely transform the architecture despite the fact that they seem very simple and kind of very innocent kind of thing over here. So I'm going to effectively, what we have implemented really with RESTnets is this kind of architecture that implements recursively this formula. Yi is equal to Fi of Yi minus 1 plus Yi minus 1. Okay. So I'm going to take this formula, and what I'm going to do with it is I'm going to write the Y3, the output of Y3. I want to write the output of Y3 as a function of only Y0 and their functions F1, F2, and F3. Okay, so I want to implement the forward pass and come up with just a composite expression that involves these two only as factors. So evidently the Y3 according to the equation is F3 Y2 plus Y2. I hope you agree. Then we have F3 of F2 of Y1 plus Y1 plus F2 of Y1 plus Y1. Didn't allow me to write it all the way, but still okay. So if I now replace the Y1 with its equal, and we are kind of done with that kind of replacement, I can write that I have an F3 of kind of a big bracket of F2. Now I'm replacing Y1 with its equal, which is F Y1 with its equal, which is F1 of Y0 plus Y0, close small bracket, plus F1 of Y0 plus Y0. This is the closing the big bracket, plus I have an F2 of Y1 over here, so I have an F2 of F1 of Y0 plus Y0 plus F1 of Y0, sorry, F1 of Y0 plus Y0. Okay, so this guy over here, is became this guy. And I want to call it also A. This guy over here became this guy. And I want to call it B. And finally, this guy is C. It's not really, I mean, even if you are not able to fully follow right now, it's just a simple algebraic kind of replacement from what we have effectively translated from the diagram we have above us. Okay, so what I want to do now is I want to take this and I want to draw it. What we see, this A plus B plus C, I want to draw it. So I want to redraw effectively what I had in the top, on the top, right? Obviously, what I'm going to redraw is the effect that the successive skip connections are having on the overall transfer forward pass equation of Y3. That's basically what I'm getting at. Okay, so I'm going to just redraw it. I'm going to start from the bottom over here, and I'm going to first draw A. So for A, I'm getting Y0 at the input, as you can see, and this goes through F1. I am adding this to. I'll map what I am just drawing right now. In fact, I just drew this guy. Then the output of that goes through F2, and what happens is there's an addition of what? Addition of this guy, which is effectively Y0 of F1 plus F1 of Y0 plus Y0, right? And this is added here. So I'm adding this, I just added this kind of term. And finally, the whole thing goes through F3, right? So this one will go through now F3. And so this kind of whole thing over here is my, oops, wrong color. This is basically my A. Okay, so this is my A. Okay, so the A will be added at some point to a B and then to a C. So what is the B? The B is F1 of Y0 plus Y0. This goes through F2, and this is my B, which is itself added to, well, I can do the addition at the end. And then finally we have C, which is basically F1 of Y0 plus Y0. So all of these are added to output to form finally the Y3. I hope you can see that. So this is B, and this is C. Okay. So what is really going on? Why we went through this kind of labor to come up with this kind of diagram that effectively conveys what's really happening. The Y0 is coming in, what is coming out as only function of Y0 and the F1, F2, and so on, in the elementary kind of gates over here, the additions. So the reason is the following. As it turns out, the main advantage that the skip connections are actually bringing is improving the diversity of paths that gradient can flow in the backward path, in the backward path during backpropagation. While without the skip connections, the gradient was going from Y3 and had a very singular path to follow to reach, let's say, Y0, and therefore all of the other kind of trainable parameters of the network, whatever those are inside F1, F2, and F3. Here, in the when we have the singular path, you have the gradient actually can go through a significant number of paths. Some of them are involving F1, some of them involving F1, F2, and F3, and some of them involving all the way to the input. A category of this kind of networks are called highway networks. So the first thing I want to mention is that the gradient flow has a diverse set of paths of various paths with gates. Of paths with gates involving F1, F2, F3, or a subset of those. Including the unit gate. And the unit gate is, if I may draw it like this, these are actually gates that involve this type of trajectories. Maybe I stick to magenta. Okay. So these are called highway networks. We'll see examples of other highway networks in other parts of the course. And backpropagation is, and therefore the gradient flow, which is responsible for sort of efficient kind of training, allowed them to actually go deeper now because earlier there were gradients were diminishing as they were going through the very much singular path. So the first layers were getting enough gradient. Again, I'm talking about the backward direction now. But the very first layers were starving. Okay, so they were not really trained, and the network was exhibiting some form of log kind of performance improvement. So gradient flow kind of greatly improved with residuals. That's the bottom line of this kind of discussion. However, there was another property which is not so evident, and the second property has to do with so some form of ensemble learning kind of architecture. So what is ensemble learning? So for those who are not really familiar with it, to some degree is associated with mixture of experts that we see in some kind of modern kind of transformer architectures today for LLMs, but not entirely equivalent. The ensemble kind of learning is based on the following kind of premise. If I may open kind of a parenthesis over here, you may have seen it in other kind of more conventional machine learning classes that you have attended. It is also known by committee methods. The premise is that you are forming, let's say, a committee to make a prediction, and this committee is some form of a kind of an additive model of the individual kind of committee member hypothesis. If you have, let's say, K members in this committee, capital K, and you have effectively you have something like that to some kind of an additive kind of model to give you the composite kind of prediction. So these guys were called in this kind of sample methods weak predictors. And they're called weak predictors because you didn't have to overinvest in them in order to get a good performance out of a committee. With enough weak predictors, the ensemble methods proved that you can actually get really good performance. In fact, sometimes, in most cases, much better than a single, very, very expensive kind of predictor, and also at the same time being more robust as well, which is, not coincidence that today's kind of best predictors have some form of ensemble learning kind of properties. Famous examples of ensemble learning for structured data are XGBoost or boosting kind of methods. And as I said, in NLP kind of space, sample properties are being these days designed in sort of DeepSeek and other kind of architectures as mixture of experts. Now, here, where is the sample kind of learning and what is really the big deal about it? So that's the kind of next kind of discussion. So in ensemble learning, what you want to do is you want to introduce some form of diversity into the committee. Like, for example, if you have a committee, like take, for example, a human committee that you're trying to get some opinion on, and you invite everyone who went to the same school, went to the same university, in any case, went through all exactly same path trajectories of learning, most likely we get very highly correlated sort of opinions in this kind of a human equivalent of a committee. And definitely you do not want to do that. And I'll explain the reason in a moment. So if you think about it like this, you have a lower bound and an upper bound in terms of performance in this kind of committee methods. So the lower bound is when you are you definitely you expect the members to make mistakes, but what you do not want to do is to make strongly correlated mistakes, right? So this is where the lower bound will be met when everyone is making exactly the same mistake at the same time. Okay, so this is something that it has some kind of math behind it, but I'm not going to go through it. The upper bound, what is really the best thing you can do, and you cannot do perfect. I mean, you obviously there's no perfection here, but definitely you can approach some very good performance with a sample kind of learning methods when you introduce diversity, as we discussed. So, for example, you can introduce diversity with three means. Either you feed to each committee member different data, in other words, via feeding to each committee member different kind of data sets to learn something different about the problem, or you apply some form of randomization. For example, one famous ensemble learning method is called random forest. Maybe some of you may have come across that in the past, or boosting methods as to gradient boosting. So the form of randomization we employ there in random forest is to pick up features and with some form of a flipping of a coin kind of probability. The third method, however, is also possible, and it's actually called using different predictors. So basically using different weak learners, y hat sub k, we can also get different opinions about an x, right? Something at the input. And this is basically what ResNet is effectively doing with the second kind of block diagram. As you can see, the ensemble learning kind of equation and the equation and the block diagram above it are going kind of hand in hand. Here I have three predictors, A, B, and C. Each one of them is offering a y hat sub k. And at the end of the day, the y3 is the summation of these y hat sub k's. So the more the blocks I add and the skip connections I add, blocks with skip connections that is, then the more the effectively the number of ensemble committee members become. And then the whole architecture is exhibiting some form of a sample learning gain, which is perhaps not evident when we first met it. So the third advantage that the residual networks are actually offering is the advantage of scalability. So, for example, it's very common to have to deal with latency as a kind of metric when you're designing kind of computer vision kind of pipelines. Some of the computer vision pipelines have to have a very strict number of milliseconds to complete a task, let's say an object detection or something like that. And featureization, it's an expensive component in any pipeline. So the ability of the ResNet to be able to chop off, let's say F3 from this kind of diagram, maintain F1 and F2, and keep all the previous kind of architecture unchanged is quite significant. So this is the reason why in many instances, next to the name ResNet, okay, next to the name ResNet, that is, you see a number where this number kind of indicates the blocks. Let's say, for example, famous numbers is like 50, even 34, 101, 150, 150. I can't remember now exactly all the numbers. 18, so when you are defining the ResNet, you're also quoting this kind of number, which is associated with the number of blocks that are in that kind of network. Yeah, so if you face a latency kind of crunch, you can actually go to ResNet 34, for example, if you are already or ResNet 50, which is a typical choice. and buy some milliseconds out of that switch, and therefore solve latency problem that you had in your computer vision pipeline. So that was basically the three advantages of a residual kind of architecture. Now, in your Python textbook, there is some more discussion of kind of dimensioning, and more specifically, all the architectural details of these guys over here, the adders, architectural details about the functions that the ResNets are engaging. And so there is a dimensioning kind of piece that I have not really covered here because I'm mostly interested for you to understand not the dimensioning is, okay, it's kind of dry discussion, okay, useful, but dry nevertheless. But over here, I just prefer to cover the principles as to why they bought us this performance improvements they have brought into the picture in computer vision space. All right, so that is a kind of what I wanted to mention tonight. I know because of the remote nature of the lecture tonight, it was a bit on the dry and kind of boring, but I do hope you got out of it. I'm going to stop now and ask for any questions that you may have.
I had a
Professor.
Oh, sorry, go ahead.
Yes, go ahead. Anyone?
Like my question is related to homework, so if you have question related to the
Oh,
class,
homework.
like
Okay, yes.
Yeah.
okay.
Anyone else non-homework questions? Then we can switch to the homework question.
I had a question about the content. So you
Yes.
mentioned that one of the advantages of ResNet was that it stops the gradient from diminishing as it's in the backward pass. I wanted to ask why the gradient diminishes and why that was a problem.
Okay. Yeah.
I'm not sure what the problem was there. Yeah.
Yeah. So, we skipped several kind of discussions on the backpropagation of neural networks, right? So we reached a point where we discussed a very elementary kind of single neuron kind of backpropagation, and but we skipped this kind of discussion about, okay, what is happening when I have, let's say, matrix by vector multiplication followed by nonlinearity and all this kind of stuff, right? So when you start putting this together, one after another, and the flow of the gradient cannot go anywhere and then go to the next block and the next block and the next block. What is really happening are two things that may be happening. One is that depending on the gate, which is inside this kind of network, you have amplification of the gradient sometimes, right? You have even explosive gradient. Depends, of course, in many matrices like W matrices, capital W matrices, this explosion is associated with the eigenstructure of these matrices. And we'll come to some discussion on this when we are dealing with LSTMs. In some other, and so depending on this eigenstructure of the matrices, the eigenvalues greater than one or less than one, you have diminishing or exploding kind of gradients. Okay, both cases in both situations are fairly problematic, with diminishing being the most problematic because when they are exploding, you can sort of clip them. Gradients can be clipped, but even then, you have sort of issues. So I cannot really give you a numerical kind of example right now on the screen, but I can point to some observations or some kind of publications talk about the sort of diminishing or exploding kind of gradients, specifically for simple architecture, CNNs like VGG, and their kind of performance, I will call it tailing off in terms of performance improvement before the residual connections got introduced.
I see. Got you. That makes sense. Thank you.
Any questions on the homework now?
Okay, so my question is related to homework, and so like my question is that um
Mm-hmm.
for each query image we need to uh return like video clips. So my question is that is this video clips refer to, and like the video clips refer to the component. So my question is this component means a combination of classes, or does it refer to one specific class? So does it mean?
As I discussed, for every image, right, you may have multiple detections, right, associated with it, right?
Yeah.
And therefore you may have, multiple semantic alignment with the original kind of video detections. And this is the so for every, let's say, query image, right, that you have in the input in the second video in the query images, right?
Yeah.
You try to come up with some kind of a similarity search, right? And in this kind of similarity search, because you are trying to return, if you like, the clip, right? You are trying to create some kind of logic behind it so that it does not report back, okay, where I have seen this image across 10 minutes, right? So, for example, an input image, which is like a front bumper, or the left door, or the right door, whatever it's actually shown there. It should have a portion of the image where the presenter is sitting there and showing the left door. It's not really like a single image out of the 10 minutes that should be returning, right? So you should be returning, if you like, some form of a window where this image of the door, right, is consistently shown. You have to translate this consistently shown rather than like just shown. So it has some kind of continuity, the video clip, right? It's almost like a segmentation task where if someone asks you, hey, do you have any details about the front door? You return, let's say, at least 3 seconds of it.
So wait, let me see.
So, for example, so this guy is, let me switch off the volume.
Hello and welcome.
So at some point he will go and, okay, he will go here. This is where most of the exterior review starts, right? So first you have
Wait,
to.
do you share the screen? I don't think you share the screen.
You don't see my screen?
Yeah, I don't see the.
Oh, is anyone else able to see my screen?
Now I see the screen. Now I see.
Okay. All right. So this is basically he shows the headlight, right?
Yeah.
So a good video clip will start from this moment, right? And it will expand into this moment, let's say. At some point after that, he will start dealing with the side of the vehicle, for example. So this is basically the output which I'm after, ideally, okay? You try to do your best to do that.
Okay, I see. So it's the combination of classes, basically.
Yeah.
Okay.
Because if your clip returns this guy over here, that's obviously not a good outcome.
Yeah.
Okay. Or any clip associated with this side of the vehicle.
And also there might be many, like some video clips that all match this. So should I continue? Should I involve all the video clips?
So the exterior review lasts from 1850 something to 2024. It's only a few minutes, right? I don't want you to return any other clip from all the 45 minutes, right? Just only the segment. Only within the segment you have to search. Only through the exterior view segment you need to be searching.
Okay, I see.
Professor?
Yes.
Do we need to for every query image, do we need to search for a particular segment or from the entire video?
No, only the exterior review video, the exterior review segment. The segment I just showed you is from 18 something to what now I forgot whatever the minute is, right? But it's only, I think, 10 minutes long.
Oh, okay. So the detections that we are gonna make on the
It's for
video
this segment, it's for
for
external.
this.
Because your data set, I thought it was for external components, external stuff.
Okay. Okay, makes sense.
Okay. Any other questions?
I had a question on the lecture today. So when
Yes.
we were talking about the REST nets,
Yes.
you mentioned they help or they overcome two of the drawbacks in the traditional CNN model, which
Mm-hmm.
was the vanishing gradient, and second was we were also reducing the spatial extent to a point where it was reduced to 1 cross 1. Can you explain a bit more how the spatial extent reduction looks in a ResNet example? And what dimensions does the output of F1, Y1 minus 1, and Y1 minus 1? I mean, are they same or are they different?
Yeah, okay. So unfortunately, I'm not able to do that right now to tell you the dimensions of, let's say, a RESTnet. But what I will do, if you put that question on, if you do me a favor, put that question on the class chat. Are you able to post questions on class chat?
Yeah,
Yeah. Put that question on class chat. Tomorrow I'll find the information. It's in your Python textbook. I think if you look at your CNN example on residual networks in the textbooks, they have the whole dimensioning exercise right there with all the skip connection dimensions. How, for example, this dimension will match to this dimension over here, because that's another problem, right? Because this guy is coming out of the input, and this guy is coming straight out of something which is compressive in terms of
yeah,
dimensions, right? So all of these details are there. I just need to find the reference section numbers and post it as an answer there so you can take a look.
sure. Thank you.
Yeah, no problem. Any other questions? All right, so good luck with your assignment. I'll see you next week, and I'll follow up with any questions in Discord if ask you watch that video. Okay, thank you. Thank you.